experimental physics in the Institute of Sciences in 1776. Only 2 years later, on the morning of February 20, 1778, Laura Bassi died suddenly after having participated in a session of the Academy of Sciences the previous evening. This woman, a forerunner of female emancipation, remains an admirable example for all women of science still today.
Okay. So, Sandra, can you share your screen and we can start with your talk?
Okay, can you see my screen?
We can see.
Okay, thank you. Thank you for the nice introduction and for the opportunity. It's a great privilege to be here and give a talk as part of the Laura Bassi seminar series. So today I will talk to you about some research that I've done with my collaborators on the topic of supermassive black hole fueling and how black holes can be fueled by gas that it's misaligned. So my talk will have two main key aspects. One of them is the study of supermassive black holes themselves, and the other one is the study of galaxies. And during my talk, I will show how supermassive black holes and galaxies are related and how we can learn about supermassive black holes by studying the galaxies in which they live. So I will start by talking about supermassive black holes. So these are black holes that have 1 million to 10 billion times the mass of our sun, and they live in the center of galaxies. And here you see this is an artistic impression of a supermassive black hole. This is the black region here, and it's surrounded by light. And this is because in some cases, when these supermassive black holes are in the center of galaxies, they accrete gas from their surroundings. And this process of gas accretion forms the so-called accretion disk. And while the gas is being accreted onto the black hole and making the black hole grow in mass, it will also result in the heating of the gas, and that will emit a large amount of energy into the surroundings of the supermassive black hole. And this emission can be detected across the whole wavelength range. So we can see signatures of black hole activity in the X-rays, optical, infrared, and radio. And we also know that black holes and galaxies co-evolve together. Black holes, supermassive black holes, are thought to be able to affect the galaxy in which they live. And this results in a very close relation between the evolution of supermassive black holes and galaxies across the whole history of the universe. So the one of the main questions that we have is, how are black holes fueled? And this so-called black hole fueling is the process by which black holes acquire their gas and therefore fuel their activity. So the fact they emit energy. So this is called the problem of black hole fueling. And we know that black holes need gas to grow. They grow in mass by the accretion of gas. But the question is, how does the gas reach the black hole? It will come from the galaxy in which the black hole lives, but the fact that supermassive black holes live in a small region of space, maybe a few times the size of our solar system, compared with the size of a galaxy, the gas needs to be able to travel through the galaxy and get to the region very close to the black hole to then be accreted. So how does this physical transport of gas occur? And also, why are some black holes active and others inactive? So when black holes are actively accreting gas, we call them active galactic nuclei, and I will refer to AGN for the rest of the talk when I refer to these active black holes. And what we know is that only a small fraction of supermassive black holes are active. If we look, for example, at the galaxies that are close to us, so the local redshift galaxies, only between 5 to 10% of supermassive black holes are active. Most of them are inactive. And the question is, what determines which black holes are active and which ones are not? And we know that black hole fielding seems to require two main ingredients. The first one is a supply of gas, and the second one is the physical mechanisms to transport that gas onto the supermassive black hole. So to solve this issue of black hole fielding, we need to figure out where is the gas coming from and how is the gas transported to the black hole. So now we'll jump into the galaxies, because this is the environment in which the supermassive black holes live, and the gas that is used to fuel the black hole is coming from the galaxy. So I will talk about some processes in galaxies that may help us understand this physical process better. So galaxies are known to interact with each other. This is an image from the Hubble Space Telescope. You can see two galaxies here that are interacting. And there are different types of interactions that can occur. For example, if you have two very massive galaxies, relatively the same size, that are merging, that's a major merger, they coalesce. But there's also the possibility that a large galaxy merges with a smaller galaxy that is a satellite, and that's a minor merger. But there are also other interactions when galaxies pass each other that can result in the transfer of gas from one galaxy to the other. So here in this figure, if you see my cursor, there's a transfer of gas from one galaxy to the other. And when this happens, we say that there's an external accretion of gas, which means that one of the galaxies is acquiring gas from its external environment. And there's some spectacular examples of when this happens. So this is, again, an image from the Hubble Space Telescope. And this is an example of a polar galaxy, or a polar disk galaxy, where you can see here in the horizontal direction, this is the stars from a galaxy. This is the original galaxy. And perpendicular to the main body of the galaxy, there's the distribution of gas and stars that were acquired from one of these external accretion events. And in this case, the gas and the stars have an orientation that it's misaligned with respect to the main body of the galaxy, and it's a misalignment of 90 degrees. So it's perpendicular to the main body of the galaxy. And that's why it's called the polar disk or polar ring galaxies. And when this happens, it's a clear indication that there was an external accretion event, because it's very difficult to produce distributions like this based on internal processes in the galaxy. So for this galaxy, as I said, there's a 90-degree misalignment, and I will be talking about misalignment for the rest of my talk. And when I say misalignment, is the angle between the original material of the galaxy, so the main stellar body of the galaxy, and the gas or stars that were acquired externally. So in this case, it's a 90-degree misalignment, but you can imagine that if you have interactions from different directions and orientations in the sky, you can end up with misalignments that go from 0 degrees to 180 degrees. So 0 degrees, it means that the material that was accreted and the main body of the galaxy are aligned, and you can have all the angles in between. And 180 degrees is a misalignment that it's called counter-rotation, and that's when the material that came from the outside and the galaxy are in the same plane, but they are rotating in opposite directions. So if you look at the direction of rotation, it's opposite between the main body of the galaxy and the new material that came in. And the question that I wanted to address in my research was, is this misalignment somehow related to the fueling of the black holes in the center of these galaxies? And the reason why I thought this was an interesting question was because we have a clear way of identifying an external accretion event. If we see large misalignments, we know that an external accretion event happened. And this means that the galaxy acquired gas. So that's already a supply of new gas into the galaxy. And looking at the observations that we have of early type galaxies, this can be ellipticals or S0 galaxies that have older stellar populations. If you look at the ones that have gas, a large fraction of them have misaligned gas. And when putting this into context, it's consistent with all of these, at least for the S0 galaxies, is consistent with all of them having acquired their gas from external accretion. So this is thought to be an important mechanism for early type galaxies to acquire gas. And if we think also about how much mass we need to power a black hole, is not that much, because black holes are very efficient machines to transform mass into energy. So if you think about the brightest active galactic nuclei that we know, quasars, we only need a fraction to maybe 10 times the mass of the sun per year to power their activity. But if we look at the more common low to moderate luminosity AGN that we know in our local universe, only a small fraction of the mass of the sun per year will be enough to power these black holes. And just thinking about the mass of a typical dwarf galaxy, could be a satellite galaxy that is being accreted, the mass that is incoming will be enough to power a black hole for a long time. So putting all this together, it could be an important mechanism for early type galaxies at least. And in addition to that, this is from the observational side, but from simulations, numerical simulations have shown that if you have the presence of misaligned structures, so stars or gas, they can promote the inflow of gas to the nucleus. And that's what you want to fuel a black hole. First, you need the gas to go to the center of the galaxy. The big question is, can this gas that is flowing to the center of the galaxy, can it fuel black hole activity? So to address this, we first targeted galaxies that were close to us, because what we wanted to study was the physical process in detail in the centers of galaxies. And we selected galaxies that had examples of this kind of misalignment. And they also had active black holes. And our goal was try to understand what is the behavior of the gas, how is it related to the black hole in the center. So one of the galaxies that we looked at, MCG 63015, here I'm showing one of the results that we obtained. This is a map of the velocities of the stars. And this is only looking at the very central region of the galaxy. One of the advantages of selecting galaxies that are close to us is we can use the current instruments that we have to look at the very central regions at high resolution. So we can distinguish motions of gas and stars in the regions close to the black hole. And this is the galaxy that we looked at. We were able to do that. So here, the black cross in the center is the position of the black hole. And the colors describe the motions of the stars. So blue represents motions of stars towards the observer, towards Earth. And orange and red is motions of stars away from us. So if you look at the direction of rotation in the center compared with the main stellar body of the galaxy here, you will see that within the ellipse, the rotation is in one direction and the main stellar body of the galaxy rotates in a different direction. The arrows at the bottom show the direction of rotation, so you can compare how the stars are rotating. And when we see this, this is called a counter-rotating stellar core, because the misalignment is 180 degrees. So the stars seem to be in the same disk, but part of them in the center are counter-rotating with respect to the rest of the galaxy. So this is a clear signature that these stars were the result of an external accretion event. So some kind of accretion from the external environment of this galaxy in the past that then originated these stars. But for the black hole, what is important is the gas, because that's what is going to be fueling black hole activity. So we wanted to also look at what the gas is doing in this galaxy. So we obtained observations of the molecular gas. And this is again, in the bottom, you can see this is the velocity map of the gas. Again, blue are velocities of the gas towards us, the observer, and red is motions away from us. And if you compare the direction of rotation of the gas with the stars, you can see that the gas is also in counter rotation. So it has a similar rotation direction as the stars in the center, which makes us think that the stars in the gas originated from the same external accretion event. And one of the interesting things is all the gas that we see in this galaxy, and this is very close to the black hole, it's all counter-rotating. So the reservoir of gas that this galaxy has to form stars or to fuel the black hole is all made of this counter-rotating gas. So we know that somehow this galaxy accreted gas from its external environment, and that gas was able to replenish the reservoir of gas that the galaxy has and got close to the black hole. Our observations allow us to see gas that got at least as close as 50 parsecs from the black hole. We also did some calculations about how much gas there is. And at the current rate at which the black hole is accreting gas and emitting energy, the mass of gas that we see here would be enough to power black hole activity for 2 gigayears. So it will be for a long time. And one curious thing that we also found was that the total amount of mass that is actually used to fuel the black hole is not that large compared with the mass used to form stars. So only 1% of the mass used to form stars was used to fuel the black hole. So this is interesting to see how the gas is used in the galaxy and how it is divided into forming stars and fueling the supermassive black hole. We also looked at another galaxy. This was also another nearby galaxy. And you can see here on the right, this is an image of a group of galaxies. And we looked at this one here on the top. And the interesting thing is that we noticed that groups of galaxies provide the right environment for these external accretion events because there are more galaxies and there are more potential interactions between them. So we looked at this galaxy here at the top, NGC 5077, and this is again on the left is a map of the velocity of the stars, the same color scheme as before. And you can see that here within the ellipse in the center, there's again a counter-rotating core of stars. So the stars in the center also rotate in the opposite direction to the main body of the galaxy. And this is again another galaxy that has an active black hole, and as previously is an S0 galaxy, so an early type galaxy. And we wanted to again look at the gas. What is the gas doing in this galaxy? And we looked at the ionized gas. And here on the right, you can see the map of the ionized gas distribution. The contours, the green contours are just to guide the eye. They are the same contours as in the left. So they are tracing the distribution of stars in the galaxy. And the white contours and the color is the distribution of gas. So you can see that the gas is completely decoupled from the stars. It's distributed almost along the minor axis of the galaxy with 2 plumes going north and south. And you can see that due to this decoupling between the stars and the gas, it's clear that this gas was accreted from the external environment of the galaxy. For this galaxy, we measured the age of the stars here in the nucleus, the counter-rotating stars, and they're very old stars. While the gas, because it's still very distributed in a way that is not stable at all, we think that it's a more recent accretion event. So in this galaxy, what we think happened was that we had 2 external accretion events. One earlier that formed the counter-rotating stars, and then a more recent one that caused this distribution of gas that it's still misaligned. And for this galaxy, we were able to look at numerical simulations that were a good representation to what we were seeing in the observation. So here I'm showing some snapshots from numerical simulations. They are showing the velocity of the gas in a galaxy. And the time goes from left to right, top to bottom. And these simulations were of two big galaxies with gas that merged. And then after the merger, the activity from supernovae was able to eject the gas in the final galaxy. That's the second step. And then later on, there was a second accretion of gas from the external environment of the galaxy. And that's the third step here. What happens to that gas is that because the galaxy has a disk of stars, the gas starts to align with the disk of stars. But this is a process that takes time. And what they see in the simulations is that first, the central part of the gas is aligned with the disk, and then the outskirts start to get aligned. And what you end up is with a warped distribution of gas that you see. And this is similar to what we see in the observation. So we think that probably in our galaxy, we are at this stage roughly, where the gas is aligning at the center. You can see that if we measure the angle, the distribution angle of our gas, we see that in the center, it is aligned at a different angle than the outskirts, which means that there's a differential alignment process going on. So the center is aligning first, then the outskirts. From the numerical simulations, the final stage of the evolution of this galaxy is that the gas will end up aligning with the stellar disk. And during this process, what happens is that the gas is losing angular momentum and it's actually being fueled to the center. So this is what we want if we want to fuel the black hole. We want mechanisms that are able to drive the gas to the center. And this is interesting because it was the first time that this theoretical scenario was seen in observations. And putting these two galaxies together, so we were able to do these detailed studies because we had the very good spatial resolution, so we could distinguish the motions of gas and stars in the centers of these galaxies. And it appears that NGC 5077, so the one on your right, is at an earlier stage of evolution after an external accretion event than the one on your left, which is MCG 63015. The gas in this one is already aligned with the disk, so we think that this is a later stage when the gas has already aligned. So probably what happens is that once you have an external accretion event, you have this process of alignment that lasts for maybe 1 or 2 gigayears, and then you'll end up with some sort of alignment. In this case, alignment, but counter rotation. The important thing is that it's a mechanism to drive the gas to the center of the galaxy from the external environment all the way down to where the black hole is. And to answer this question, it's nice to have these two examples that we can study in detail. I mean, there are other examples in the literature that have been studied like this. But what we wanted to do was to do a statistical study, statistically significant study to see if there's actually some relation between misalignment and black hole fueling. And this is a difficult problem because of the numbers, the fractions of galaxies that we have. So AGN, as I said in the beginning of the talk, are only present in a fraction of galaxies, and also galaxies that go through interactions and have misalignment are also a subset of all the galaxies that we can study. So if we want to do a statistically significant study, we need to start with a very large number of galaxies. So what we did was to use a sample of more than 3,000 galaxies from the SAMI survey. This was a survey done in Australia, and they made available several products from the survey, and these are excellent products to work with. And for our specific goals, this was very convenient because there was information that could be used to make 2D maps of the velocity of the stars and the gas, similar to the maps that I showed earlier in the talk. And there was also information that will allow us to determine if these galaxies had active black holes or not. So our goal was to use this sample to determine what is the fraction of active black holes of AGN depending on the misalignment. Do we see more AGN in galaxies that have misalignment or not? So the way that we did this was similar to the analysis that I showed previously. So we had maps for the velocity of the stars and the gas. You can see here on the left is an example of a stellar velocity map. This is for the same galaxy. And on the right is the gas in that galaxy. And what we did was to measure the axis of symmetry for these velocity maps and determine the misalignment between the stellar and the gas rotation. So in this galaxy, this is an example of counter rotation. So the rotation is misaligned by 180 degrees. You can see that there's red, blue, while for gas is blue, red. So this is complete misalignment. So this is an example of one galaxy, but we did this analysis for the entire sample. And so we determined the misalignment angle between the stars and the gas. And then what we did next was to determine what is the excitation cause of the gas. And this could be an AGN, or it could be star formation or liner. And this is low ionization nuclear emission line regions. Doesn't have to be in the nucleus. Could also be outside the nucleus. And we divided our galaxies into these three categories. So liners can be low luminosity AGN, but they can also be tracers of shocks or an older stellar population. So we decided to keep these three categories separate. But we were mostly interested in what the AGN were doing, the galaxies with AGN were doing. So then what we did was to separate galaxies into the ones that were aligned and the ones that were misaligned. And we used a cutoff angle of 45 degrees because we wanted to make sure that the galaxies that we're looking at were really misaligned and not aligned, but with some errors. So between 45 degrees and 180 degrees, that's what we called misaligned galaxies. Will be shown here on the right, and on the left, these are the aligned galaxies. And what we did was to calculate the fraction of AGN in each one of these groups. And what we found was that the misaligned galaxies had a higher fraction of AGN than the aligned galaxies. And this is a difference between 7% and 20%, and is significant at the 3 sigma level. So this was the first time that this effect was seen, and it shows that active black holes are relatively more common in galaxies with misalignment, which shows that there's some relation between the presence or the formation of misaligned structures and the powering of black holes. And we looked at the liners separately, but we also saw the same trend as for the AGN. And this makes sense if the liners are tracing low luminosity AGN or even shocks, because we expect if you have an external accretion of gas, that there will be some shocks between any residual gas that is in the galaxy and the gas that is coming from the outside. And here on the right, I just put all the different types of gas excitation together so you can see the relative contributions of AGN, liners, and star-forming galaxies. One thing that we needed to check was, is this gas that we see, the kinematics of the gas misalignment, being caused by outflows in AGN? Because we know that AGN are able to drive outflows. We wanted to make sure that the gas that we were seeing was coming from the outside, so external accretion, and not being driven outwards by the AGN. So what we did was to measure the average velocity dispersion of the gas. And this is typically used to identify outflows. So outflows tend to have very high velocity dispersions. So what we did was to analyze the samples, divide the samples into misaligned AGN, aligned AGN, misaligned galaxies, aligned galaxies, look at their average gas velocity dispersion. And we did some statistical tests to see if the samples were consistent with being drawn from the same population. And we basically didn't see any difference between the AGN, misaligned, aligned, or the misaligned galaxies. So this means that the gas that we're seeing is not being driven by an AGN outflow, but it's actually coming from the outside. So the velocity dispersions of the gas are relatively low for AGN and for the galaxies. What we also did was to separate our analysis into a galaxy morphology, because we know that early type galaxies tend to have a higher frequency of these misaligned structures. So what we did here was to divide in the left figure That's the analysis for early type galaxies, and the right side is late type galaxies. So late type galaxies typically have more gas, younger stars. And you can see here that most of the AGN, Liner, star-forming galaxies are all in the bin corresponding to aligned stars and gas. And while for early type galaxies, it's a broader distribution. So the majority are also in aligned galaxies, but there's a tail of AGN, Liners, and some star-forming galaxies that have strong misalignments. So early type galaxies seem to have misalignment more commonly observed. And this is something that was known before. And the reason why is that if you have a late type galaxy that has a lot of gas and there's some external gas accretion occurring, if the gas that is coming in is coming in a less quantity than the gas that you have in the galaxy, there will be dissipation and any misalignment will be very short-lived. While in early type galaxies, since they typically don't have as much gas to start with, if you have an external accretion of gas, then the misalignment will be significant in terms of the total amount of gas in the galaxy and will be long-lived. So that's one of the reasons why this trend was expected. And it's probably much more important for early type galaxies and for the fueling of the black holes and the star formation in there. So let me conclude. So I talked about supermassive black holes, their fueling process, and how is that related with processes occurring at the galaxy scale. So whenever there's an external gas accretion event, there's the possibility to build or replenish the galaxy gas reservoir that it can then be used to fuel the black hole or to fuel star formation. And I've shown results, and these were the first results that have shown that stellar to gas kinematic misalignment is connected with a higher fraction of active black holes. And this means that this may be an important mechanism to fuel black holes because it provides the two ingredients that we need, a supply of gas and the dynamical mechanisms to drive that gas to the black hole. And this mechanism will be in particular important for early type galaxies that have more of these misalignments. And we also expect this effect to be stronger as you go to higher redshift, because at higher redshift, there will be a higher fraction of galaxy interactions. This sample that we're looking at is low redshift, so we can extrapolate that at a higher redshift. This is probably a mechanism that will be more significant for the fueling of supermassive black holes. Okay, thank you.
Thank you, Sandra. Congratulations, very good talk. And if there are questions, please raise your hand and tell us. In the meantime, Elias, no, is clapping only. And I have a question about the redshift. When you have the distribution that you have shown that you found more AGN in the galaxies that have misalignment than, or also the liner more present, there is a segregation in redshift in the sense that might be the more distant, also if it is a low redshift sample, or the redshift is doesn't matter.
I actually haven't separated the bins into redshift bins. I just put them all together. The redshift bin, I can show you the range of redshifts that we used in the sample. So it's 0.004 to 0.095. And I put them all together just because the numbers of AGN are not that high. So to have a statistically significant result, we had to put them all together. But it's actually a good idea to check if there's some trend in redshift. I could make, maybe two bins and just see if there's something there. But I haven't tried that. That's a good idea. Thank you.
Okay, good. And now there is Maurizio Paolillo. Please go.
Hi, Sandra. Thanks for the nice talk. I was wondering, you said that you cannot see evidence that misalignment is due to outflow. But are there cases in which you both see the outflow and the misalignment, or one prevents to see the other?
That's a good question. So there may be some nuclear outflows. So what we've seen in one of the galaxies that I showed, NGC 5077, was that we had this large-scale gas falling in, but then in the center we had an AGN-driven outflow, but it didn't go that far. It went out to, if I remember correctly, 1 kiloparsec, but then it wasn't affecting the rest of the galaxy. So you can have both. And in this particular sample that we used, we actually excluded the central PSF of the observations that corresponds to 3 arcseconds, is like a 1 kiloparsec for each galaxy, just to exclude these unresolved AGN-driven outflows in the center, because we wanted to see what is responsible for the large-scale distribution of gas. And that seems to be gas coming from the outside and not AGN outflows that are able to drive gas all the way out to the galaxy. So there may be some unresolved AGN outflows, but they're probably very nuclear, so 1 kiloparsec distance at most. But we haven't, because we don't have the resolution, we can't really say if they're present there or not.
Thank you.
Elena, Razia?
Yeah, so a curiosity. So you mentioned the importance of this work for the high redshift. So at the same time, I was wondering, the high redshift, there should be also a higher density because the cosmological density is simply higher. So are you able in your sample to create a subsample on the base of the environment density? So because probably, I mean, if you are in a dense environment, you also have more than one single merger. So as you said, there was one case, I think you mentioned that there are evidences that there are, two mergers subsequent. So I was wondering how the picture could change in that situation.
Yeah, no, that's an interesting exercise to do. So for this sample, one thing that we were able to do was to separate between cluster galaxies and field and group galaxies. And we saw that the trend that we see in AGN as a function of misalignment was driven by field and group galaxies mostly. So the cluster galaxies didn't have that trend. So probably if you have a much denser environment like a cluster, you may not have these interactions driving gas to the black hole, but it seems to be more frequent in groups. Now, in terms of the redshift evolution, I would assume that galaxies go through, as you were saying, several episodes or several mergers or interactions. So maybe we will see several events like this ones that I was showing, that you have gas accretion, you fuel AGN for a certain period of time, then you have another one and you fuel the AGN again. So it's likely that this happens many times. So what we're trying to work on now is to expand this study to higher redshift and see if we can, we're observationally limited, but we can go to a little bit higher redshift and see if we can make any conclusions about that. Just based on the fraction of mergers, we would expect them to be much more frequent at higher redshift. So I would expect, based on that, that this mechanism would be more important then, but we still have to do it observationally.
Okay, thank you.
Alessia?
Ciao, grazie. I had many questions actually. One, you already answered about the environment, but I have other two. First one is, if you go back to MCG 63015, and you look at the molecular gas distribution, it seems to me that you have a hole close to the center.
Yeah, that's true.
Isn't that a signature of a kind of feedback from the AGN, as Maurizio was saying at the beginning, or not? Or is a problem in the data or whatever?
Yeah, it is a problem in the data. So we couldn't detect molecular gas at a high enough signal to noise ratio. But that could also be just because we have an AGN in the center and it's inherently difficult to measure, absorption lines or emission lines very close to the black hole. So we can't really say if this is a hole. My guess is that it's due to the low signal because of the AGN. But I know that from CO observations, colder molecular gas, it's actually present in the center. So I would assume that the H2 is also present, but not detected in these particular observations.
Okay, thanks. And if I can, I have another one.
Right, go.
Using SAMI data, did you ever find any connection between the presence of the AGN and the presence of a stellar bar? some kind?
Oh, very good question. I haven't looked into that. I think I would need to look into the images and try to find if there are some bars there. But that's a good question. I should try to do that.
Because that's something that could fuel the AGN. No, it's one of the things that can.
Yeah. Even I would even expect, that to not be related with the external accretion event, but also like a secular process. But that's a good idea of something to try to do with this sample. If the images have quality enough to detect the bars, that's a good idea. The data set is also public. So it's something that if you're interested in doing, I think it would be great as well, because it's, the data set is amazing. So you can just dive into it and look for these trends.
Thanks.
And Angela Iovino now.
Yes, just first of all, thanks for the very nice and clear talk. So just a very simple question. Did you try to check if there is any correlation between the presence of this misalignment and the velocity dispersion of the groups? Because, there is usually this sentence that in clusters, the high velocity dispersion prevents, the interaction to be long time, and therefore to have time to strip gas and to take gas away, let's say. So, maybe in groups, this is a more common phenomenon. And then I wanted also to ask if you have any evidence from images of tidal gas visible or something like that. If there is any trace of this eventual possible merger event that triggered this phenomenon.
Okay, so for your first question, I haven't looked at the dispersion of the groups. So you're saying that there will probably be some kind of trend between the how long-lived these structures are and the velocity dispersion of the groups, but I haven't looked into that yet.
It is usually said that the interaction happen more easily, let's say, in groups than in clusters because of the velocity dispersion relative between galaxies.
Well, we see that just separating groups and clusters, we see that in groups we have this trend, while in clusters we don't see it. But within the in the groups of groups, I haven't looked into any possible trend. The groups that have higher dispersion or the ones that have lower dispersion, I haven't looked into that. I've only separated clusters from groups, but that's something to look into. And your second question,
if there is evidence in the images of
yes, there was actually a study that was published just a couple of days ago where they looked at the images for the SAMI survey, and they found, yes, that many of them have signatures of past mergers and interactions. Of course, that they also noted that they're only sensitive to the ones that are the brighter and the more recent ones. For example, if you have minor mergers, they wouldn't be able to identify any kind of tidal features or anything like that. But they detect some signatures of major mergers in the galaxies that have misalignment. So at least part of the sample, there's some signatures in the images that some kind of interaction occurred.
Thanks a lot.
Okay. Any other question? If not, we thanks again, Sandra, for the very, very nice talk, and see you next month for the next Laura Bassi talk.
Thank you.
Thanks.
Bye-bye.
Bye-bye.
Thank you. Bye.
Thank you.
Bye.
Thank you, Sandra. Very interesting.
Very, very good.
Thank you very much.
Thank you.
Thank you very
Bye.
much.
E Daniela, puoi stoppare di YouTube.
Sì, ok, lo faccio. Ok.